All right, welcome to week 8 of CNET 50B. And this week we're going to talk about chapter 21 and RC and RL transient responses. So the topics here are RC charge and discharge, RC time constant, the universal time constant chart, then the RC exponential equations, then the L over R, the inductance over the resistance, time constant, exponential equations, and then long, medium, short time constants, and then an integrator and a differentiator. All right, so both capacitance and induction offer an opposition to a circuit parameter. So the capacitor is going to cause a change in voltage, and the inductor is going to cause a change in current. So remember that the capacitor is voltage and the inductor is current. So this chapter, the focus is going to be how long does it take for the charging and discharging of the capacitor or the expanding and collapsing of the magnetic field in the inductor. All right, so just relate back to when we talked about capacitors and when we talked about inductors. Now, what is their time factors? All right, so to determine the amount of time with the capacitor, so let's start with the capacitor. You must determine the time constant, and for this time constant, it's the product of the resistance times the capacitance. And RC is denoted by the Greek letter tau. So tau equals R times C. Now an inductor, the time constant is L, the inductance, divided by the resistance. And that will be the time constant for an inductive circuit. All right? Now, a time constant is the time needed for a change of 63.2% in the voltage across the capacitor or the current through the inductor. Because remember, capacitors are talking about voltage, inductors we're talking about current. Now in addition, the time constants also allow us to examine the transient response in series RC and RL circuits and determine how steady state conditions are reached. So the transient response is a temporary condition of a changing voltage or a current that exists only until a steady state value is reached. And that response is associated with non-sinusoidal voltage and current waveforms, for example, square, rectangular, and triangular, and when a DC source is switched on and off. Now the effects of inductance and capacitance on non-sinusoidal waveforms is to produce a wave shape change. So what that means is that depending on the time constant, RC and RL circuits are used to provide filtering, wave shaping, and timing. So in our DC circuits, like we mentioned last week, the capacitors on a video card, that's all DC, right? Our power supply converts AC to DC. So on our motherboard, all of our voltage is DC. And that's what the capacitors are doing, is shaping the signal. Okay? Now capacitors are really small, very easy to manufacture, inexpensive to make, so they're good devices to work with in those type of circuits. Now, if you have a voltage divider circuit containing resistance and capacitance is connected by means of a switch, it's called an RC series circuit. So here we have the resistor here, and then the capacitor here. Let me erase that. So, and then we have the resistor here, and then the capacitor right here. So that's an RC. So when you first close the switch at time equals 0, the voltage at the source is going to be whatever it is at the source. And then over time, the voltage will go down. After a certain amount of time, the voltage through the capacitor will equal the voltage across the source, which will mean the total voltage will go to 0. Okay? So 21-1 shows the charging circuit. 21-2 is the discharging circuit. So in that charging circuit, if the circuit didn't contain a capacitor, the voltage would have ceased at the instant the switch was moved to the discharge position. Because the capacitor is in the circuit, voltage is applied to the circuit until the capacitor is discharged completely at T1. So at the moment of, or instant of discharge, the capacitor's discharge path is typically a smaller resistance than its charge path. This means that the first instant of time, the capacitor can support a large discharge current through the load as demonstrated by the VC RL ratio. So if you look at that circuit, let's go back here, whatever the voltage across the capacitor over the voltage at the resistor. Now when we first turn this on, all the voltage is in the resistor, and then over time it all goes to the capacitor. Then when we discharge it, all the voltage is here, and then it will slowly go to the VR and discharge. Okay, so here, boom, it goes up. All right. Now, a common application for this high discharge current is a flash bulb for a camera. If you remember on the old cameras that had flash bulbs, the flash bulb needs more current to ignite that the small camera battery can supply. So there's a capacitor in there, and you press it, and you normally would hear this, right, and it snap off, which would then utilize the bulb. Okay, now the time required to charge a capacitor to 63.2% of maximum voltage, or to discharge this 36.8 of its final voltage, is known as tau. And tau, when we're charging, to get to 63.2 is 1 tau, and then to get to fully charge is 5 tau, and then to discharge to 36.8 is 1 tau, and then to fully discharge is 5 tau. And remember, tau equals, in a capacitive circuit, R times C. And then in an inductive circuit, it's L divided by R. Okay? So that's the idea of tau there. Now, after 5 time constants, the accumulated voltage across the capacitor is approximately 99.3. Now, for practical reasons, it's considered fully charged at that time. The charge continues at a rate of 63.2% of whatever voltage is left. Okay? Now, note that tau is a unit of time, and as we will see later, for every unit of time, this charge accumulated on the capacitor is 63.2% of the source minus the capacitor, the VC. So if we have mega ohms and microfarads, it's going to 10 to the 6 times 10 to the negative 6 will be in seconds. If you're kilo ohms and microfarads, you're in milliseconds, and then mega ohms and picofarads, you're in microseconds. All right, so it's just our multiplication there. So what is the time constant of a 0.01 microfarad capacitor in series with a 2 kilo ohm resistor? We just multiply those, and it comes out to 20 microseconds. So this week's homework will have formulas where you'll calculate RC, tau time factors, and RLR time factors. So what is the time constant of a 10 microfarad capacitor in series with a 10 kilo ohm resistor? So again, it's just 10 times 10 to the negative 6 times 100 times 10 to the third, and that comes out to 1 second. And then what value of series resistance is needed to cause a tau of 1.2 milliseconds with a 4.7 microfarad capacitor. So now for that you just go tau equals RC, therefore R equals tau divided by C. So 1.2 millisecond divided by 4.7 microfarads will give you the resistance there. So you can calculate those. These are just calculator problems that you can do. All right. Now, the voltage waveform produced by the capacitor acquiring a charge is known as an exponential waveform. So if we look at this curve, that's exponential, right? That shows exponential growth and exponential decay. And the exponential value is based on the natural logarithm, or E, which is 2.71828. Now we'll see where this comes into play later, but for now just remember it's exponential. Now there's also a universal time constant, so that says as the source voltage, so the source voltage and the values R and C in a circuit are usually known, a universal time constant chart can be used to find the voltage or current values for any amount of time. So here's the charging circuit, here's the discharge. So this is charging, this is discharging, and that will give us the values there. Okay? So curve A is a plot of the capacitor voltage during charge or the inductor current during growth, and then B is the discharge or the decay. Right? Now the time scale is graduated in terms of the time constant so that the curves may be used for any value of resistive, capacitive, or resistive inductive. And all of our RC and RL are going to follow those curves. That universal curve is going to apply. Okay? So you can look at some of these values here in the book and find that. So let's look at this. If you have the 50 kilo ohm resistors connected in series with a 40 microfarad capacitor with a DC source of 50 volts, what is the charge across the capacitor after the period of 6 seconds? Assume VC, excuse me, assume that VC starts at 0. So if you look at the values here, you just multiply this and you get 2 seconds, and 6 seconds is going to be 3 taus. And then if you go to the chart, 3 taus, so here's our taus here, right? So at 3 taus you're approximately a little over 90%, and that's what, so here's 3 taus, 95%, and 95% of 50 volts is 47.5. So it all just kind of ties in together here. All right? And then here's some more values there. And the universal time constant chart provides a graphical approach to solving series RC and series RL formula. This is because interpreting the percentage from the curves is easier for whole number multiples. So you can use that to get a real good ballpark of what's going on there. All right, now another formula that we can use to calculate the capacitor voltage at any point along the curve is this equation 21.2, which says the voltage across the capacitor equals the source voltage times 1 minus E raised to the negative t over tau, where t is the time interval for charging, and then tau equals RC. So if we had a 22 kilo ohm resistor in series with a 0.002 microfarad capacitor, and the voltage is 12 volts, what is the charge at the capacitor after a time of 160 microseconds assuming VC equals 0 at time equals 0. So to calculate that, first you have to calculate tau, which is just RC. So that's 44 microseconds. Then we're going to take 12 volts, because that's our source voltage, times 1 minus negative E with the negative time, which is negative 160 times 10 to the negative 6, divided by our tau, which is 44 e to the negative 6. So if you take negative E times that, you get 11.68 volts. All right? So here's the steps that you need to use on your calculator. So on that Sharp calculator, you take 12 parentheses 1 minus second inverse, and then you do e to the negative 160 exponent negative 6 divided by 44 exponent negative 6, end of brackets, equals, and you get 11.68 volts. All right? So in the book, there's always going to have these steps how to use your calculator. So if you're struggling with these equations, the book shows you exactly how to do those. And when I do the homework solution for this, I'll show you the calculator steps on that as well. All right? So let's say we have a 500 ohm resistor is in series with a 0.068 microfarad capacitor and a 10 volt battery. What is the charge on the capacitor after a time of 82 microseconds? So again, first you calculate the tau, which is RC, and then you take 10 times 1 minus the negative time, which is negative 82 times 10 to the negative 6, divided by tau, end of brackets, equals, and that comes out to your value there. Okay, so then here's another one with that, and you can see that you can calculate this without any problems. All right, so then here's the calculator steps again, and it just keeps going. So if you know that the current, now this was for current, the second one, IC equals V over R, because that's a capacitor, because current equals voltage divided by resistance, whereas voltage equals I times divided by R, and you get the answers there. All right? So I'm going to skip through this until we get to the time constant for an inductor. Now remember, a capacitor is talking about current or voltage. The inductor is dealing with how long it takes for the current to charge. Okay, and the formula now is tau equal L divided by R. So instead of tau equals RC for an inductor, it's L divided by R. So if you look at this, what is the time constant of a 10 Henry coil with a 100 ohm of series resistance? You just divide them. So 10 Henry divided by 100 ohms equals 0.1 seconds. And then the same thing for this one, and so forth. Now note that the time constant is directly proportional to the value of the inductance and inversely proportional to the circuit resistance. Thus, a greater inductance or a smaller circuit will increase the time constant. Now you've seen how there is a high discharge current. The first instant of time when a capacitor is discharged, there's a somewhat similar response in an inductor. There's a high voltage, much more than the source voltage, produced when the magnetic field of the inductor collapses as the circuit is open. And the relationship for the exponential is the current of the inductor equals the source voltage divided by the resistance times 1 minus the exponent natural log of negative t over tau. So here's some formulas that will go through that and calculate the instantaneous current and the instantaneous voltage. All right, So that's going to get us through chapter 21 here. And there's a couple slides here that are right out of the book that talks about long, medium, and short time constants. Talks about the integrator. So an integrator is used to wave shape. So this is accomplished by a series RC circuit in which the output is taken across the capacitor, which is also known as a long time constant circuit, and that is what is used to convert waveforms. All right, and then so here, if we have an input of a square wave and take the output across the capacitor, it's going to vary at low frequencies. It's going to still be a square wave. At medium frequencies, it's going to be a sawtooth, or and then at high frequencies, it'll be a sawtooth or a triangular output. All right, and then a differentiator is where you take the input goes across the capacitor and then you measure it across the resistor, and in this case at low frequencies it's going to show that decay, right? And then at high frequencies it will start to look more like the original. All right, so that is the information that is contained in chapter 21 of the textbook, and you can let me get here. So that shows us all of the information that we need for chapter 21, the RC and RL transient responses. All right, and then of course homework 8, which you'll pick up in week 8's lab, will be due next week when you turn in the lab. You'll turn in homework 8 next week when you start lab 9. So same time period that we've always been on. All right, take care, and I'll talk to you later.